Okay, perfect. So thank you very much. I'll have to apologize for not being in presence in Ettenheim, but unfortunately, due to a cold, I was unable to travel to Ettenheim and do the speech. So it's my pleasure to do it online. And just to give you a short impression who's talking. So that's me. Actually, I studied electrical engineering in Stuttgart, then did my PhD at the Institute for EMC at TU Braunschweig, and since then working for different vendors of measurement equipment in the same role, so meaning application engineer for digital debug tools. But fortunately, as we've learned today already, never lost the focus on the EMC topic. So today, the major focus will be on which measurement instrument will give you best or better details on your current application and when to use which instruments. So giving you some ideas when to use a spectrum analyzer or a oscilloscope. So first, I'd like to introduce how an EMI receiver or a spectrum analyzer is operating and what are the basic block diagrams there. Then give a difference between full versus pre-compliance, pre-selection, RBW filters, detectors, also with different sweep modes. And finally conclude with the oscilloscope, so where are the differences and what can still be measured with an oscilloscope or which analysis could be done. And we've already seen some very nice examples today there. So for an EMI receiver versus spectrum analyzer, what's the base construction? If we are looking at the spectrum analyzer, we're seeing, okay, there's an input attenuator, we have some low pass there that's restricting the higher frequency components. And then we have a switchable variable gain amplifier. And then we are already in the conversion stages. So we are always based on a frequency mixing process. So that's why it's called a heterodyne or super heterodyne measurement approach. And afterwards, we are working in a digital domain. So we are having the ADCs and nowadays instruments, and then these filters and so forth. In comparison, a EMI receiver is not only a spectrum analyzer with something in addition. It got more or less these additional blocks up front. So those are not equivalent, even though we still have some limiters and also some attenuators at the beginning. But the most important thing is this pre-selectors. So these frequency switchable filters. And these pre-selectors, we'll come to that in a minute, are very valuable in terms of suppression of high power disturbers close to smaller signals on our DUT side. Afterwards, both instruments, the spectrum analyzer and EMI receiver, are doing the same. So we're having the mixing process and still later on the display of the different measurements there. Summing it up, the EMI receiver has the highest dynamic range. It's very robust against pulses, especially when using the pulse limiters and the attenuators. And that's very important. If you go for a full compliance later on, we'll have these CISPRA EN conform receivers, detectors inside. And therefore, we have a drawback of this architecture. It's the low analysis bandwidth in comparison to what could be done in spectrum analyzers today. Still, the dynamic range of a spectrum analyzer is quite good. We have a high analysis bandwidth, and we have fast measurement times due to the implementation of these FFT-based analyzers today. But the detectors are not CISPR compliant. And of course, there are some models available with a pre-compliance option where you could get a calibration of those. But nevertheless, you will still be missing the pre-selection of the EMI receiver. So please always be careful, especially in power applications. The pre-selector is of high value there, and therefore it's always worth to think about the difference between EMI receiver and spectrum analyzer and to keep that in mind. So what's the pre-selector if we look at the operation? So in this example, we see we are having here some peaks, and we'd like to only separate this one in the middle. And if we have a pre-selection filter, we are neglecting all the power outside of these. So those are neglected and thus will not contribute to any power that is seen by the mixers and the amplifiers afterwards. And therefore, the amount of energy provided to the front end is way lower and thus we have a higher dynamic range afterwards. So the mixer level is going down, and thus the dynamic range that could be achieved is going up. How to interpret it? A preselector in general is a filter bank. These could be switched automatically based on frequency, and filters are wide enough to not reduce the desired frequency range so that we can measure them all together, and we have the high dynamic range. If we look in the data sheet, we'll see there's a whole bunch of these filters integrated, and in dependency of these different bandwidths we'd like to measure, those are switched afterwards, and we see this. These are fixed bandpass filters. For higher frequencies, we are just suppressing the lower frequency noise, let's say it like that, and thus only having the YIG filter, which suppresses all frequencies below the 8 gigahertz at the ESW. If we are going to our signal flow diagram of the measurement receivers, we are seeing our input. Then we could decide AC or DC coupling if you'd like to have a switchable attenuator selected, and in dependency of the frequency range, we are seeing there's a 150 kilohertz to 30 megahertz preselector currently active, and then going to the preamplifier, which is switched off, and afterwards to the analysis stage. And here it's always worth to have a look there, because it's very good to double check if your signal flow is like you are expecting it, and you are not having any additional filters added that would make the measurement cumbersome. For these calculations, if you'd like to do a estimation of your dynamic range, you could see there the dynamic range indication of for a narrowband signal, the wide band with and without these additional preselectors, and you're seeing a significant increase for wideband disturbing signals, and it's only worth to talk about a preselector when you're having these more or less wideband disturbers, so meaning having some higher frequency components, so meaning higher in amplitude, meaning higher in power, that is provided to the mixing process, and therefore we'll have to suppress these higher harmonics or higher side emissions to accurately measure the amplitude of these other emissions there. If we go for a filter shape, the EMI receiver typically offers only a Gaussian filter shape, and for a spectrum analyzer we could also have some different filters there. The EMI receiver has a 6 dB definition, and we'll come to that in a minute, while the spectrum analyzer has a 3 dB. And then the EMI receiver has this standard conformance receiver bandwidths implemented, so the 200 hertz, 9 kilohertz, 120, and 1 megahertz. While for the spectrum analyzers, typically we have these 1, 2, 3, 4, 5 sequence, so meaning each decade you could select 1, 2, 3, 5 hertz, then afterwards 10, 20, 30, 50, and so forth. Regarding the filter shape, so the spectrum analyzer here in green, we're seeing the 3 dB filter is wider, so meaning we are having these filter bandwidth achieved at a minus 3 dB attenuation, while for the yellow trace we are seeing it's deeper, thus more selective. And as we are seeing, the pulse or the filter shape is opening up to the ground. So if we think about the noise floor accumulated inside these filter shape, we are seeing that these 3 dB filters accumulate more noise than for these 6 dB filters. So that's why the EMI receiver has a higher sensitivity and higher selectivity itself. So the sensitivity because we are suppressing more noise, and the selectivity thanks to the filters. So these deeper filters are beneficial for doing a higher separation of the frequencies that are occurring next to each other. How are these RBW filters then realized? So if we are thinking about these mixing processes, we are getting our signal from the ADC. We're getting those then filtered with or down converted with the demodulators, and then we are adding these filter coefficients, and afterwards we're getting it displayed on the screen. So for a peak detector, you could think about this is something like a storage into a capacitor, and we have a switch there for unloading it. And the peak detector always displays the max peak there, which is then hold. The quasi-peak has a time. So we have here this RC, and the detector time typically in the range of larger 1 second to see how often a signal is present or not. And then last but not least, the traditional average detector. And these are the 3 most prominent detectors. And if we are thinking about in short examples, so we are seeing from this PWM signal, the wider the gap gets, the quasi-peak will lower down to the average value. The peak, of course, stays at the peak level. And if we are getting a shorter interval for this 0-1 switches, let's say like that, then we are seeing the quasi-peak goes up to the maximum peak voltage. So we have a direct indication if this is more or less a short term or so meaning if we have a high repetition rate, like in this example on the right, or if we have a short repetition rate, that's the example on the left. And therefore, it's quite good to know that the peak will always be the maximum and the average will always be smaller or equal to the quasi-peak. And the quasi-peak will wander up or down in respect to the repetition rate of the pulses occurring at the input of the receiver. We have different sweep modes in today's analyzers. So one is the traditional step mode. So meaning we're going through the complete spectrum by having one frequency, waiting for the settling time, doing the measurement, then going for the next frequency, waiting for the second settling time, doing the measurement, and so forth. So at each measurement point, we'll have to wait for the measurement time. And if we go for the more modern architectures where we have the so-called swept mode. And for the swept mode, we're continuously going through the spectrum and then varying the frequency components and doing the measurements there. So it's important to keep that in mind. In swept mode, we are continuously varying the frequency, while in step mode, we are going there from one frequency to the next in discrete steps. And last but not least, the time domain scan. So what to understand there? If we think about our spectrum, we could slice the spectrum into smaller portions, and these smaller portions are then investigated by using a fast Fourier transform. So we are measuring first of all the time domain signal, then doing a transform of the signal, and then we're getting the frequency components of this specific spectrum out of the analysis. And therefore, we are reducing the sweep time dramatically because we are always taking a whole or a number of frequency at one shot, then doing the next shot, and so forth. So we have the speed improvement as we have less measurement times that have to be used for the different frequency points. And we have a higher probability to capture these more or less singular events that are occurring or could occur. So if we compare the sweep times for these different bands, we are seeing we're going easily down from the minutes or hours range to some milliseconds or seconds. And that's a quite tremendous speed up in doing the measurements. For the peak detector, we have a broad frequency range, and we could also use the limit lines and then get a list there of our different peaks that are available. So we are seeing there what are the values on the frequency axis, on the amplitude axis, if we are below or below or above the limit line. And last but not least, you could also define later on some test automation so that these tests will be repeated afterwards in the quasi-peak detectors. So typically we are starting to do the measurement using the peak detector and measuring the peak against the quasi-peak threshold. And as we've learned previously, the quasi-peak will always be the same like the peak or below. So vice versa, if the peak value is below the quasi-peak threshold, we don't have to repeat the measurement with the quasi-peak value because the quasi-peak will be below this value we have already measured. And that's very important if we think about the measurement times. So for the peak, we are typically talking about settling times in the milliseconds range, so 50 milliseconds, something in that range. While for the quasi-peak, typically 1 or 2 seconds per frequency point are chosen. So we're way faster in doing the peak measurement than for the quasi-peak. And this is still valid also for the FFT analyzers. So even if we are doing these measurements in the peak, we could use a smaller time window and do more measurements per time. That's why it's very convenient to do so. And what could now be done? If we go through, first of all, we have a scan, then we have a peak search. This could either only plot the peak list we've previously seen, or afterwards, we could define to have a final measurement, and this measurement will then do the analysis on the peaks that have been above the threshold for the quasi-peak, and then display these final results afterwards. We could also, and shall not forget, to define the correct frequency ranges, so which ranges have to be measured, according to which standard, and also which filters shall be used, then for peak search and final measurement, like stated before. And also very nice, if you have an automated listen for the switch between these different phase combinations, you could also integrate the switch inside the firmware of the ESW, and therefore remote control the listen from the measurement receiver. What else is done? So we could also do a logarithmic frequency sweep, analyze lower frequencies in more detail. So we have a better distribution of the measurement points. If we think about a wide frequency sweep that goes from close to DC up to 1 gigahertz, and we would distribute maybe 1,000 points, we would get there a certain step size, which would be 1 megahertz in this case. So we would have 1 megahertz as lowest frequency point and then going up. That's why we're talking typically about this logarithmic frequency sweep. So to get at least 1 point per decade part here, to be sure not to forget any of these low frequency components. Also, we have the demodulation capabilities. We have some IF and zero span modes, as well as real-time functions inside. What's very nice to see is the spectrogram. So to get a time domain scan and the representation there of the spectra and the time, so the amplitude over time. And we're seeing now the amplitude is coded in color. So we're seeing the time on the y-axis and still the frequency on the x-axis. And in this video, we're seeing a car that's blowing its horn. And what's very nice to see is for a short term, we're seeing there, these are the short blowing the horn. And then afterwards, we have the long horn going there. And you could easily differentiate which effects are coming from which portion. So that's why the spectrogram also in the oscilloscopes is very worth to do, to have a look on. So jumping to the oscilloscopes. What first of all is the huge difference? So we are talking for the oscilloscope at the connector, there's the probing, of course, a connector cable, an antenna or something like that. Then we are having some attenuator amplifier, and then we are going directly to the digital domain, especially for the RTO class of Rhodian Schwarz. And then there is the so-called digital trigger system, which has some huge benefits in comparison to the analog one. But if you're interested there, please send us a message. We'll be happy to come back to you there later on. And afterwards, we are displaying what we've captured on screen, or we are also adding some digital signal processing functionalities. So doing some measurements, maybe some averaging, low pass filtering, and so forth. What's the major difference when comparing the architectures? So in the oscilloscope, we are operating purely in time domain. So we are measuring from DC up to the corner frequency of the instrument, and we don't have any mixing processes inside. So we have no chance to do a pre-selection like for the measurement receiver. And therefore, we're doing in comparison the narrowband measurements with an ERI receiver And we are having the oscilloscope as a broadband measurement device. So having the instantaneous view from DC to the corner frequency with one shot. And of course, the filters, we'll see that in a minute. So we could adjust an RBW filter, and there we are not compliant to the EMI standards. From the use model, like you've seen in Artur's presentation, we could define a start-stop frequency. We could also define a resolution bandwidth. These are, of course, 3 dB filters, not 6 dB filters. But for the debugging process and finding the root cause of EMC, this doesn't matter. We only have to consider that we are accumulating more noise from the bottom of the noise floor of the instrument, and that's the hugest difference. We also have a chance to do some mask testing in the time as well as frequency domain, and that's very helpful if we'd like to do some automated testing there too. What's happening inside the oscilloscopes? So for a traditional FFT, we are doing some time domain measurement. We're going through these windowing function that was defined. We are calculating the FFT. And if we are restricting the analysis region, so we are restricting the start-stop frequency, that's just a pure software zoom. So in most cases, we will lose resolution, and therefore we are limited in our analysis later on. That's why the colleagues in R&D came up with the idea, why not let the frequency domain control the time domain? So having that said, we're first of all adjusting the time domain to meet the zoom requirements of the frequency domain, and therefore we are adjusting the time domain signal to meet our frequency requirements afterwards, and therefore we are not losing any resolution in the frequency domain, and we are capable of doing also narrow bandwidth solution, and that's called also the spectrum analyzer model. So these are quite helpful to keep in mind. So please don't be afraid if you're using an R&S oscilloscope there that the frequency domain is adjusting the time domain. You still have the chance to use a zoom function to get still everything you'd like to see on screen. Another feature included in our firmware is that we have this overlapping. So typically we are not doing a single FFT per acquisition. We are slicing these FFTs into smaller portions because we cannot handle that much points that are integrated in the memory. And therefore we are displaying even on a single acquisition several FFTs. And these are per standard overlapping with 50%. So we could see a nice evolution of our energy over time in the signal, and we'll have some example later on there. In addition, we could also use some average or RMS detectors. We could change the units. We could use mask tests for the max hold functions. And for the debugging itself, I can only recommend to use small record bandwidths, so just to increase the responsiveness of the instrument. If we are using the FFT, and we've seen that also in our Artur's demo, we could also use the gate functions of the FFT, so that we are using, for example, a zoom window or a cursor. And then by moving the cursor, we could differentiate between the pulse and the ringing itself to see which components are issued by which effect and time domain. From the debugging workflow, first of all, of course, you'll have to activate the FFT. Afterwards, you could adjust the signal bandwidth, so to match your needs. Maybe you'd like to see some smaller or do some analysis smaller than 100 kilohertz. So then you're using the bandwidth. You could also use a zoom and of course a peak table. So in this case, we are then also measuring against the threshold and listing all these different frequency components in the table. To give you an impression, what's the difference between an oscilloscope and the EMI measurement receiver? We did a short example, having a center frequency of 1 gigahertz. We are having 2 carriers with a spacing of 100 kilohertz generated in the SMBV 100B. And both are attenuated in 60 dB in amplitude. So meaning one carrier is 60 dB above the next one. Afterwards, we provided the signal to a power splitter, and the same signal was provided to the EMI receiver and the oscilloscope at the same time. So if we are comparing, first of all, the full span mode. So we used a 3 gigahertz RTO there, and we used a 3 gigahertz span of the EMI receiver. We are seeing these two peaks. So therefore, no difference yet in the instruments, and everything seems to be quite equal there. When adjusting to the frequency range that is of interest for us, so going to 1 gigahertz, and using there also only a sweep width of about 100 kilohertz. The same for both instruments. We're seeing, okay, there's the major peak, and there's also the harmonic, but the smaller the peaks are getting there, so we see some side emissions of the generator, the better is the EMI receiver. So at a certain point, we of course have some lag at the oscilloscope due to wideband noise. So that has to be considered. We are still talking about a wideband front end, but nevertheless, we are able to differentiate between signals that are 60 dBc next to each other. And if we are looking at these different components, if you have some more experience, you see, okay, there's no noise between these curves. So these will be more or less CW signals that are always present, while for all the others here, we see some noise going there in the ground floor. So there's not at all times a signal present. So, and that's the huge difference. We have small band signal filters, while we are seeing this integration of noise and side emissions in the oscilloscope. So not saying that the oscilloscope is worse, but there we are seeing the limitation of not having a frequency selective instrument, and therefore we are not suppressing these higher emissions that good. Summing it up, as a short guidance as mentioned, the hugest difference between EMI receiver spectrum analyzer is the filter shape, as well as not having a pre-selector. So the pre-selector at the EMI receiver is always available. But nevertheless, we have a high selectivity. And for the oscilloscope, we have also the 3 dB filters. It's very important to keep in mind we are measuring down to DC. So not close, we are really measuring DC. And we could do some mass testing in frequency and time domains to do a correlation between time and frequency domain. We could do gated FFTs. And like we have seen at the beginning, for the multi-channel coherent receiver we have with this oscilloscope, you could use up to 4 channels at a time, and therefore do some very helpful cross-correlation between measurement of some direct voltage running on the lines, maybe some antenna and the near-field probe set to do a correlation where your EMC issues are coming from. Giving it a short grouping, of course, if you are interested in a full compliance, then you'll have to use an EMI receiver at the end, because there nothing else is allowed. You'll need the CISPR compliant detectors. But the more you're going for the pre-compliance and EMI debugging, the spectrum analyzer, as well as especially the oscilloscope, are highly recommended. And as we are talking especially about power applications in this webinar series, in most cases, you'll have your oscilloscope already mounted on your desk. So my highest recommendation to you would be, please think of using your FFT inside the oscilloscope, because nearly every oscilloscope that has been sold in the past 15 years has a more or less usable FFT implementation. So at least you'll be possible to, or able to see if there are some frequency components running around in your design that you might not expect. And if you don't have these nice near-field probe sets that have been showed several times today around, you could also use easily a passive probe by just connecting the crocodile clamp of the ground connection to the inner conductor of the hook of your probe. And then you also have a very low-cost near-field probe that could be used for some close investigation. But please don't forget, you'll have a ground lead. This will be ground of the oscilloscope. So please don't short circuit anything on your design by going around with this near-field probe approach. So which instruments would be of interest? So for the oscilloscope, of course, we're talking about the oscilloscopes from the RTO class today in the presentation. So what capabilities are in. But nevertheless, also the smaller instruments like the RTBMA have a very powerful FFT implementation. And now you could also draw a waterfall plot. So it's very helpful also for debugging. And of course, we also have our value spectrum analyzers like they're called, like the FPL. And these are also very helpful for starting in the EMI debugging. And the closer we are going to the compliance over our ESRP, we are going to the ESW for full compliance measurement receiver. If any further questions are coming up, so please also don't hesitate to contact us. And even if you're not coming from Germany, we will redirect your request then to the local sales office. So thank you very much. Are there any questions?
So are there any questions? So let's start with the first question. What is the main difference and advantages between an EMI receiver and a spectrum analyzer?
The main advantage of the EMI receiver is its pre-selector. So having the chance to have a filter before the first initial mixing stage, which will suppress the higher power spectra components outside of the analysis region of this portion of the frequency range we are looking at.
Thank you very much. So the next question is, can you spend a few words to the VBW setting related to the RBW 9 kilohertz, 120 kilohertz setting?
That's a good one and a very tricky one. So the RBW filter itself is the filter which is mounted in our mixing stage. So when we're doing the analysis, if you think about the block models, then we have there the radio bandwidth filters. And if we'd like to further decrease the displayed noise, then we could add these video bandwidth filters. And these would then have to be in the same range or smaller than the radio bandwidth filters to cancel out the noise like in averaging. So two different methods. The video bandwidth is only affecting the displayed signal and thus averaging out the noise there. While the RBW is directly on the physical layer, if you'd like to say so. So meaning in the mixing stage and the analysis stage then of the EMI receiver or spectrum analyzer.
Thanks a lot. So the next question would be, can you please share the types, names of all devices, analyzer and oscilloscopes?
So for the oscilloscope, we could take any of the instruments in our portfolio for doing this base analysis. So meaning an FFT is included in all of them. If you'd like to do analysis with more than one gate, then you'll have to have a look at the RTE, RTO, or RTP family of oscilloscopes. So this gate functionality takes a lot of calculation power. Therefore, only the higher classes of oscilloscopes have these included. And for the analyzers, we used an ESW as a measurement receiver. And for all other instruments, the FSW or the ESRP as pre-compliance measurement receiver were introduced in the slide set. But if you'd like to get more information there, also please feel free to contact your local sales representative and we'll be happy to come back to you then.
So if there are any more questions, please type them in the Q&A button at the bottom of your Zoom webinar interface. So I cannot see any new questions coming in. So thank you very much, Alexander, for the presentation. I want to remind everyone.
Was my pleasure.